Hey programmers, welcome back. Right now I want to show you a solution in Python for this sum list problem. So I'll jump right in and I think we'll start with the iterative version. I'll show you also the recursive version later on. And so to solve this one, I do want to accumulate a total sum. So I'll create that variable, just call it total sum, set it equal to 0. I know by the end of my function I'm going to return that total sum number. And then I need to lay down the foundation for my just classic linked list traversal. So I need some variable, I'll call it current, initialize it to the head. And I know that the main boilerplate I need is to iterate while current is not none. And the important code I need is to set current equal to current not next. So just this code, basically the variable of current and also this while loop, is a really core pattern for linked lists. And then from there, how do I actually want to utilize my current node's value? Well, all I want to do is just take current.val, and I should just really take it and add it to total sum. Just increment it. So I'll say total sum plus equals current val. This should be a fine solution, nothing fancy at all. So we'll give it a shot. A few things I do want to emphasize about this implementation. Typically for my linked list problems, I always like to write my iterative code just like this. A common mistake I've seen students make in the past is to sometimes preemptively write logic about current next. In other words, it's not going to be too useful to write patterns like this, right? Current dot next dot val. Instead of looking ahead in the linked list, you should only really worry about your current node itself, because depending on the length of the actual linked list, you may not actually know if there's a valid next node. So always try to stay very present in your code, right? That's why my base case is about current and not current.next, right? And that's why when I add the value, I'm not saying current.next.value, right? It's about staying very present. That way you don't make any assumptions about the length of your input list. So this is the very classic iterative version. Now let me show you how you can do this one recursively. I think the recursive solution is really elegant. And so we'll start with our base case. We always know our base case is going to be when head is none. And so when head is none, I like to think about my base cases as if they're their own inputs, right? So if head is none, that kind of means that I have an empty linked list. What's the total sum of a empty linked list? Well, it's definitely just 0. That's my base case. And I know I'm going to need to recurse here, so I'll say sum list. And I'll pass along the next node in the sequence, right? Head.next. I know that if head.next is none, then I'll just get back 0. But if it's not none, then I need to do some computation, right? I know this call, it's going to return to me the sum of the remainder of the linked list, right? With everything else in the linked list. I'm going to take that and add it with my value, right? My value is head.val. And I would just return that quantity. This is really all we'll need for this recursive sum list solution. So let's give that a go. I should get the same behavior. Do bear in mind, when it comes to the complexity of this, time complexity is going to be the same as our iterative, right? It's going to be O of n, where n is the number of nodes, because we make a recursive call for every single node. And the space complexity of this is actually also going to be O of n because of all of the stack frames we add to the call stack, right? To even perform any recursion, your programming runtime is going to need to actually add that information onto the call stack. And so we will consider this a linear time and space. All right, programmers, so before you hop into the next problem, I want you to practice both the recursive and iterative flavors of this, and I'll catch you in the next one.